This video is about simple harmonic motion, which is motion involving a body that oscillates. Simple refers to lack of complication. Alright, to start with, I'm drawing a simple swinging clock. It's a good example of an everyday oscillating object. The part that I'm shading in now is the rest position or equilibrium. It's marked B. Points A and C represent the maximum displacement or positive and negative amplitude from the rest position. One oscillation is when it travels from A to C and C back to A. The clock uses a driving mechanism which ensures it will oscillate for a long time. What I'm drawing now is a displacement time graph for a free oscillation which has no driving mechanism. You can see that it eventually will stop. What I'm drawing now is a displacement time graph for a driving mechanism, like the clock. It will not stop oscillating for a long time, as you can see. Alright, these are just some keywords now. Displacement, or x, is measured in meters, and it is the distance an object moves from its mean or rest position, and it may be positive or negative. Amplitude, which is x subscript O, is measured in meters as well, and it is the maximum displacement, and it will always be positive. Frequency, or F, is measured in hertz, and it is the number of oscillations per unit time at any point. And finally, the period, T, measured in seconds, is the time for one complete pattern of oscillation to take place at any point. As you should know, period equals 1 over frequency, so therefore T equals 1 over F. When talking about circular motion, one oscillation corresponds to one full rotation of a circle. This is 2 pi radians. If there are f oscillations per unit time, there will be a corresponding angle of 2 pi f radians per unit time. Therefore, the angular frequency is 2 pi f, and you may see this as omega. Energy in simple harmonic motion. So there's a person on a swing. For no particular reason, we're going to call him Rory. There are 5 points to be labelled on this diagram. A and E represent the maximum displacement from the rest position or equilibrium, which is labelled C. For one complete oscillation, Rory, starting from A, has to swing all the way to E, and then all the way back from E to A. Labelling point C on the diagram is equilibrium or the rest position. This is where displacement is 0. At points A and E on the diagram, where displacement from the rest position is at its maximum, there is also a maximum gravitational potential energy. At point C on the diagram in rest position, or where displacement is 0, there is maximum kinetic energy. Starting at point A and heading towards point B, there is a fall in gravitational potential energy and a rise in kinetic energy. Going from point B to point C, gravitational potential energy continues to decrease to 0, whereas kinetic energy rises to its maximum. Continuing from point C to point D, kinetic energy decreases and gravitational potential energy starts to rise again. From D to E, kinetic energy decreases to 0 and gravitational potential energy is increased to maximum. This is only half of the oscillation. Using a green line to represent kinetic energy, starting from maximum displacement, where energy is 0, you can see that as displacement is decreasing, energy is increasing to its maximum. Now using the purple line to represent gravitational potential energy at maximum displacement, you can see that it has maximum energy, but as displacement decreases to 0, energy also decreases to 0. The white line just drawn represents the total energy in the system. Once again, green is for kinetic energy and purple is for gravitational potential energy. Using green to represent kinetic energy again, and purple to represent gravitational potential energy again, this diagram is showing that as one energy makes a gain or a loss, the other energy makes a corresponding gain or loss. Or in other words, the total energy in the system has to remain constant. So as gravitational potential energy is decreasing, kinetic energy must be increasing, and vice versa. This next bit is all about resonance. So resonance is simply described as the build-up of a large amplitude oscillation when the frequency of vibrating objects match. For resonance to occur, there has to be at least two vibrating objects. There is one object that's causing the effect, with a frequency that is called the driver frequency. There is also the driven object, which has a natural frequency of vibration. A large amplitude oscillation is built up when the two frequencies are the same. This effect is called resonance. The line on the left is the amplitude of the driven object. The line on the right is the amplitude of the driver. The line where they meet or equal is called the resonant frequency. This graph shows the effect of damping on the resonant response of an oscillator. When damping is applied to a resonating object, it has two effects. Increasing the amount of damping reduces the amplitude of the driven oscillation, and it also slightly reduces the frequency of the driven oscillation. The green line represents zero damping, where nothing is being damped. The purple line represents light damping, where you can see the amplitude has decreased slightly. The orange line represents heavy damping, where you can see that the amplitude is even lower and the frequency has also decreased. The red line is even heavier damping, where the amplitude is even lower and the frequency is also decreased. And this last line is more or less critical damping, where there's almost no amplitude and hardly any frequency. This was the Tacoma Narrows Bridge. It collapsed in 1940 due to resonance. As you can see, the bridge looks very rubbery, and it should not look like that. It was battered by very high winds for hours on end, until eventually it found the resonant frequency, natural frequency being that of the bridge, and boom! Rest in peace, dog. And the car. Sad face.